So today we will start with the introduction of the NAND gate. So if you look at the figure, so this is the logic diagram of a two-input NAND gate where the input is X and Y, okay, and the output is C, and C is equal to X dot Y whole bar. And now if you have a three-input NAND gate, so now this is the logic diagram of a three-input NAND gate, and this is the logic diagram of a four-input NAND gate. Okay, so this is a two-input NOR gate, diagram of a three-input NOR gate, and it's a diagram of a four-input NOR gate. Okay, now let's assume we have the following function: f is equal to bd plus a bar cd bar. Okay, so can anyone tell me what kind of expression is this? Is it a SOP expression or POS expression? You may use your mic. Anyone tell me, is it a SOP expression or POS expression? Yes, I need your help.
It's a SOP expression.
Yeah, it's a SOP expression. Yeah, so it's a SOP expression. So what we are going to do, so now let's assume if you say that this is an expression. So now what I'm going to do, so this is an expression, and what is the expression? So f is now using the red color for this. So f is now, if you look at this expression, so f is equal to bd plus, I'm using the green color, but a bar cd bar, a bar c d bar. Okay, so this is a sum of the product expression. So now if we draw the diagram for this, so we are using the AND gate for BD. So now the B and D are the input. So okay, this is my first term, and then we have the green color. So the input is A bar. For this A bar we need an inverter. Then we have C, and then we have D bar. So now we have D bar. And now what we are going to do, we are doing the sum of this. So basically, can you see here? So this is now the sum of, this is the sum of the two terms. So now we need an OR gate, and my output is now F. Okay, now if you look at this logic diagram, so this is actually what we called it, this is called as the SOP expression. So this is my SOP expression. So whenever we are giving a SOP expression, so we can easily convert this SOP expression, into its NAND implementation. How? Let's see. So we can easily convert this into its NAND implementation. And how can we convert this into a NAND implementation? So we do some tricks. What are those tricks? So let's see those tricks. What we can do, so if this is an expression, so what we can do, so we can put a bubble on the output of the first bubble on the output of the first AND gate. Okay, so we can, what we can do, so now what I'm going to do, so I'm now using the purple color, the blue color. So I can put a bubble on the output of the first AND gate and a bubble on the output of the second AND gate. But, and then to counter its effects, we need another bubble here, this bubble here and this bubble here. So we put a bubble here because these two bubbles will cancel out each other. Now, if you look at here, which gate is this now? So this, now we have converted this AND gate into a NAND gate. It's already inverted. So this is a NAND gate now. And now if you look at the black color, this is already a NAND gate. But if you look at this thingy, the thingy which is shown in the yellow color, so this is now a negative OR gate. So negative OR gate. Okay, now we have, for this negative OR gate, we have bubble on the input side. So if we have bubble on the input side, if we want to push this bubble onto the output side, this will be converted into a NAND gate. So now how can we convert this circuit into a NAND implementation? So now we have the first AND gate. This is this gate number one. This is gate number one. And then we have the second NAND gate, which is the green color. So this is the second NAND gate. So can you see? Sorry, this is three input NAND gate. So this is the gate number two. And now what we are going to do? So now we are converting the red color into another NAND gate. So when we push these bubbles on the output, so it will be converted to a NAND gate. So now my output will be F. Got it? So so in this way we can easily convert a SOP expression into its NAND implementation. Any question? Okay, so is it clear, Rex? Is it clear? Please answer me. I will call the names.
Sir.
James. Okay, very good, very good. Okay, now I'm giving another example. So now we're going another example. So let's assume we have another function. Let's assume we have a function, and let's assume we say k. So can we see? Let's assume we have another function k, and k is actually we can say ab plus, and then we have a bar c plus, and then we have c d. Okay, so is it a SOP expression or false expression? Is it a yes? And you'll tell me.
So,
Is this a SOP expression? So can you see? Let's assume we have these three terms. So now let's assume we have A, C, and D. Okay. So now what we need? So we need and the first AND gate, which is actually AB, which is the black color. And now we have the another AND gate. So this is actually this is A bar, and then this is C. And for the first one, it is actually A and B. And for the blue one, so if you look at the blue one, so this is actually A, C, and D. And then we combine them. So we combine them with the OR gate. So this is the sum of the. So now this is my output K. Okay, how can we convert this into its NAND implementation? So what we do, so we put a bubble here. So now what I'm going to, I'm now using the purple color. So we put a bubble here, we put another bubble here, we put another bubble here. And to cancel out this effect, we put all these bubbles on the input of K. Okay, so these are already, so now if we convert this into its NAND implementation, so this is gate number one, which is actually A and B, which is again the other gates, which is actually A bar C, A bar C. And then we have the blue color, which is actually ACD, ACD. And now since we have the bubble on the output side, so now we have the bubble on the output side. So we have the first bubble, and then we have the second bubble, and then this is already named gate. And now this is now my third bubble. Okay, now we can convert this yellow thingy. We can convert this yellow thingy into a NAND gate implementation. So what we do? So we now I'm now using a red color. So now can we see here? Again, we convert this into a NAND implementation. So can you see here? Now, please remember this is very important. So if you look at here, so for this thingy, this is actually so can you see here? This is actually the whole thingy is what? It's a SOP expression. This is a SOP expression. Okay, now if you look at here, this SOP expression is actually which logic? This SOP expression will lead to my AND OR logic. So this is AND, we have the first level of AND gate, and now the second level of OR gate. Okay. In the absence of these bubbles, so it will give me an AND OR logic. We have the first level of AND gate and the second level of OR gate. But when we convert this into a NAND implementation, so this is now the NAND implementation. So this is now the NAND implementation of the SOP expression. Any question? Any question? Is it clear? Yes, please answer me. Anyone can answer.
yes, please.
Okay, so now we have a two-level AND OR logic. So can you see here? Now this is function. This is a SOP expression. This is the first AND gate. This is second. So this is called as the AND OR logic. The first level is the AND logic, and the second level is the OR logic. Okay, if you want to convert this into a NAND implementation, so what we need to push the bubbles on the output of this AND gates and the input of the OR gate, because these two bubbles will cancel out each other. So now this is a negative OR gate, and we can convert this negative OR gate into a NAND implementation. So this is a two-level NAND implementation. The first level is now a NAND gate, and the second level is also a NAND gate. Any question? Any question? Should we proceed? Okay, so now this is the SOP implementation. This is the NAND implementation of the SOP expression, and the SOP expression can be implemented using the AND OR logic. The first level is the AND level, and the second level is the OR level. Okay, now if we want to convert a circuit into its NOR implementation, so for NOR implementation, we need to convert the expression into POS expression. So now can you see here? Now this G is equal to A plus D. Okay, now I will explain this in an example. So now this is another example. So now what I'm going to do, Control A, and then deleting it. So now what is my expression here? So now if you look at my expression, G is equal to A plus D. So now we are using the red color. G is equal to, now can you see here, A plus D, A plus D. And now I'm using the green color for the other thingy. So now if you look at the green color, B plus C plus D bar. B plus C plus D bar. Okay, now if you look at this thing, so now this is actually now if you look at here, this is a pos expression. So this is a pos expression, product of some expression. And it will lead me to first OR gate. So now can you see here, this is actually A and D, which is the black color. And now we have the other OR gate for the blue color. This is actually B, C, and D bar. And D bar. And then we have the output. On the output, we have NAND gate, which is actually G. Okay, now if you look at this thingy, so the first level, can you see here, this we call this as OR, and the second level is AND. So this is called as OR AND logic. Now what we are going to do, because we want to convert this, so we want to convert this into, because this is a pos expression, and we want to convert this into a NOR implementation. When we want to convert this into a NOR implementation, what we can do, we can put a bubble here. So now a bubble here, and now we can put on the bubble of the second NOR gate, and then we have, okay, since we have put a bubble on the output gate, so now we have this NAND gate. So to cancel out this effect, so we also put a bubble here. So now we can put a bubble here, we can put a bubble here, and now this is my output G. Now if you look at here in this yellow color, this is actually a negative AND gate. And now we have the bubbles on the input side. When we push the bubble on the output side, it will be converted into an OR gate, NOR gate. So can you see here? So now if we convert this circuit back into this thingy, so now we have the first. This is the first NOR gate, which is actually A and D. Then we have the second NOR gate, which is actually the second NOR gate, and the input is B, C, and D bar. And now we have converted this AND gate into a NOR gate. So now, so can you see here? Now in this case, now the first level. So this is actually my what level? This is my NOR. And now we have second level, so this is the NOR implementation. So if we are given a pos expression, so we can easily convert that pos expression into a NOR implementation, and if you are giving a SOP expression, we can easily convert that SOP expression into its NAND implementation. Any question? Any question? Should we proceed? Yes, I want answer from anyone, please.
Yes, Professor.
Yes, Professor.
It means, okay, maybe if I'll call any name and the student is not present, I will mark him as an absent. Okay, so please be attentive. So now can you see here? So now please look at here. So now we have the first level. So this is a two-level OR AND logic. The first level is the OR gate, and the second level is the AND gate. So now what we do, we insert bubbles. We insert bubble on the output of the NOR gate and the input of the AND gate, because these bubble will cancel out each other. And now in this case, now the first level is already a NOR implementation, but now we need to convert the second level, which is a negative AND gate, to its NOR implementation. When we push this bubble on the output side, it will become the NOR. So now this is the final NOR implementation. It's the two-level NOR implementation of the POS expression. So this is the POS expression. The first level is the OR gate, and the second level, so it's also called as OR AND circuit. And then the final implementation is the NOR implementation. Any question? Should we proceed? So, okay, now we want to study some of the property of the exclusive OR gate and exclusive NOR gate. So exclusive OR gate is an important Boolean function which is used extensively in Boolean logic. So there are two type of gates. One is exclusive OR gate, and another is exclusive NOR gate. Okay, so now this is the truth table. On the left hand side is the truth table of the exclusive OR gate, and on the right hand side is the truth table of the exclusive NOR gate. Now can you see here, exclusive NOR gate is also known as an equivalent circuit. So now can you see here, now in this example, so we can say, okay, so how can we okay, so now can you see here? So now please look at here. So this is now what I'm going to do. I'm copying this, Control C, putting it in pen. Okay, now in this example, exclusive NOR gate. So okay, now in this case, are the inputs equal or not equal? Can you tell me? Yes, in this case.
Yes.
They are equal. So when they are equal, the output is 1. So it means if they are equal, so in this case, the inputs are equal, so the output is 1. And now in the green color, so the green color, the outputs are not equal. So not equal. So if the output is not equal, so the output is 0. Okay. So exclusive NOR gate is also called as the equivalent gate. Clear? And now these are some function properties of the, okay. Now please look at here. Okay, now this is an exclusive NOR gate, the exclusive OR function. So this is exclusive OR function. So can you see here? So the exclusive OR function. Now let's assume if we have this thingy. So we have this function f. Let's assume we have function f. F is equal to now x exclusive or y. So we can, if you do the SOP expression for this, it is actually equal to x bar y plus x bar x control z. So x y bar. Any question? So this is actually what's it? Is it a SOP implementation or POS expression implementation? So it is called as the POS SOP implementation. Okay. Now if you look at here, let's assume we have f1 and now we have f2. So this f1 is actually the exclusive OR gate. So this is exclusive OR gate. This one f1 is now an exclusive OR gate. Now if you have this f2, so can you see here f2? So now this is my f2, which is actually x exclusive or y whole bar. So this is which gate? This is now an exclusive NOR gate. And if you want to convert this into the SOP implementation or the SOP expression, so the SOP expression for this will be xy plus x bar y bar. Got it? So this is the SOP implementation. This is the SOP implementation of exclusive NOR gate. Any question? Any question? Is it clear? So can you see here the exclusive OR function? So this is exclusive OR function. So on the left hand side is the exclusive OR, and the right hand side is the SOP implementation. So now this is the SOP implementation of the exclusive OR, and this is the SOP implementation of the exclusive NOR gate. Okay. And these are some of the property of the exclusive OR and exclusive, and you need to memorize all of these properties. Okay, please remember this is very tricky and very important. Okay, so now let's assume if we say, let's assume if we say that now there is a function f. So if we say f is equal to, so let's assume this is a function f, and if we say this function is s exclusive or x y exclusive or z. So this is a function, and if I ask you to draw the logic diagram in exam, and if someone draws this logic diagram, he will get 0. Please, this is x, y, and z, and now we say this f. This is wrong because there is exclusive OR gate. Please remember, exclusive OR gate is a 2-input gate. It's a 2-input gate. So how can we convert this function? So so now for this we need an exclusive OR gate. So can we write this something like this? X exclusive OR y. So this is my black color. So I can also write this k exclusive OR z. So what is k now? K exclusive OR z. So now we need an exclusive OR gate. The output is f, and the input is k and z. But now what is k? K is actually what now? This is actually x. Any question? Any question? Is it clear?
Yes.
Okay. Now let's assume we have another function. Now I'll use different colors now. Let's assume we have another function. Let's assume we have this function f. and then we say, yeah, f is equal to a exclusive or b, okay, and then I'm now using exclusive or, and then we can say c exclusive or d. So now conceptually we can write, okay, if someone will draw this diagram in the exam, he will get 0, because this 4 input exclusive OR gate does not exist. A, B, C, and D, and if we say F, this is wrong. This is wrong. How can we draw it? So how can we write F? So we can write F is equal to, so F is equal to, now can we say, we can say K, and then we can say, oh, now then we have an exclusive OR, and then we can see M. So now what is F? F is K exclusive OR M. So now we need an exclusive OR gate, which is the black color. So now this is the black color, this is the black color. My output is F. The first input is K, which is the red color. And now we have the second input, which is M, which is actually the blue color. But what is K? K is actually A exclusive or B. So now we can see here. So now we have an exclusive OR gate for this. So this is A and B. And now we have an M, and M is actually C or. Any question? Any question? Yes, is there any question? If it's not clear, please let me know. Maybe some of the students, they slept. Yes, Ghala, Haura, Junaid, Kaiser.
No questions, sir. No
Professor.
questions.
Okay, good. So if there is a question, you can interrupt me at any time. Okay. Now we want to implement another function. So now this is an exclusive OR function. Let's assume if you want to implement another function f. So let's assume we have f is equal to a exclusive or b exclusive or c whole bar. So this is actually the exclusive NOR function. So what we can do, so now we can have, so if someone will draw this diagram in exam, he will get 0. A, B, and C is wrong. What we can do, so how can we draw it? This is, please remember, this is tricky. So we can write. Okay, now what I'm going to do, so now I'm using different colors because colors are always good. So I can redraw it like this: A exclusive or B, and then I can do, then I can use the green color exclusive or C, and then I can put the blue color, which is whole bar. Okay, can I write something like this? So can I write something like, so this is K, which is the red color, and now we have an exclusive or C, which is the blue color, and then we have a bar, which is the blue color. So can you see here, this is exclusive NOR gate. So it's exclusive NOR gate. So this is now an exclusive NOR gate, and F is the blue color. So F is the blue color. So now we have an exclusive NOR gate. The output is bar, so this is bar here. Okay, and the first input is K, which is the red color. So this is my K, which is the red color, and L, C, and C is the second input. So this is my C here. And what is K now? K is now a. Any question? Clear? Okay. Now, what we are going to do, now we are studying the OR function. What is an OR function? And please remember, this is very important. This is very important. Okay. So what is an OR function? Okay. So in this particular example, so we want to compute so what is an OR function? So first we need to define the OR function. The OR function, the output is 1 if the number of 1 is odd in the input, and the output is 0 otherwise. Okay, so if the number of 1s are odd in the input. So can you see here? Please look at here. Now, for this particular example, now can you see here? Now f odd. Now we have a function f odd. So this is my odd function f odd, and it is a function of 3 variables. What are the name of these 3 variables? Can you tell me, please? Yes. Quick. It's a function of 3 variables. What are the name of these variables? Yes.
X, Y,
Correct.
Z.
X, Y, and Z. So it's a function of X, Y, and Z. So f odd is now a function of 3 variables. So it is a function of 3 variables. And then in this case, n is 3. Now my n is 3 now. So if n is 3, so now we have to respond n. which is actually 2 to the power n, which is actually 2 to the power 3, is equal to 8 combinations. Okay, now we want to count the number of ones here. So now what we are going to do, so now we want to count the number of ones here. So now can you see here the ones, the number of ones, the number of ones. How many ones are in the first table? Yes, and how many ones are there? 0, 1. How many ones are here? 1. And can you see here? Here are single one. Here in this example, there is also single one. Okay. Now I will now use the blue color. How many ones are there in there? How many ones are there? 2. Can you see here? Now how many ones are there? Here there are 2 ones, and here there are also 2 ones. Now can you see here? Now we have this black color, and now using the black color. And how many ones are here? There are 3 ones. Yes. Okay. So now if you look at here, now here in this example, so in this example, can you see here? So now here in the this one, and this 3, all of them are odd or even? Odd. Any question? Okay. Which entries are even? Which entries are even? So this is odd one. So can you see here, since the number of ones are odd, so in this case we have the output is 1. So it's odd, so the output is 1 here. So for these entries, so the output is 1. So can you see here these outputs and these outputs, and here the outputs are 1. And for this, the first entry. So now how can we write f odd? So f odd, if we want to write this into the sigma m form, so sigma m, the sum of them in terms. So can you see? Can you tell me how can we write it in m form? Help me. Yes. Anyone?
X naught, Y naught, Z.
No. I can write it in m form, sigma m form.
1, 2,
1. Very good.
and 7.
No. 1, 2. This is 1, 0, 1, 2, 3, 4, 5,
4 and 7.
1, 2, 4, and 7. Am I right? Okay. Now can we write here? So now can you see it is actually m1 plus m2 plus m4 plus m7. And what is m1? So please remember m1 is, can you see here, it is 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 1, 1. So can you see here, this is what, so now since it's a function of, so it is actually x, y, z, so x bar, y bar, z, plus x bar, y, z bar, plus x, y bar, z bar, plus x, y, z. Am I right? Yes or no?
Yes.
Okay. Now if you do it, so now what are you going to do? So now we have found this expression. So now this is found expression. Can you see here? So now this is the expression. Okay. Please look at the color coding that I used. Okay. Now please look at here. This is 1. 1 is the red color. 1. So this is actually x bar, y bar, z. The black color 2. It is 0, 1, 0. It is actually x bar, y, z bar. And the blue color, it is actually 1, 0, 0. So it is actually x, y bar, z bar. And the green color 7, x, y, z. Any question? Okay. Now please look at here. This is very important. This is very important. So what I'm going to do now, I'm going to copy this, and then I'm going to paste it here. Okay. Now we have this expression. Since we have this expression, okay, what is common in the first 2 terms? What is common here? In the first line, x bar is common. So what should I write? Y bar z plus what? Y z bar plus what is common in the second term? Help me. X is common, and then you can say y bar z bar plus y z. Okay. Now can we write something like this? So actually, please remember, this is very important. So this is actually can you see here, this is x bar, and what is this thing in the red one? So now this thing, it is actually y exclusive or z plus x and then you can say y exclusive or z whole bar. So can you see here, this thingy is an exclusive OR gate, and this one is an exclusive NOR gate. Okay, can I write something like this? So can I write something like this? So this is actually equal to x bar. Can I write y exclusive or z x bar k plus x k bar? And what is x bar k plus x k bar? It is actually equal to x exclusive or k. And now what is my k? K is actually y exclusive or z. So now in this example, now what is k? So k is now in this example y exclusive or z. So now can you see here x exclusive or y exclusive or z? Okay. Now if you look at here, can you see here this thingy, the whole thingy? SOP implementation or POS implementation? Help me. I need your attention. No one is replying. Yes. Is it a SOP implementation or POS implementation?
So
It's a SOP
SOP.
implementation.
It's SOP implementation. Yeah, it's a SOP implementation. So it's a SOP implementation. And then if you look at this thingy, this whole thingy, the last one, which implementation is this? Can you tell me? This is an exclusive OR implementation. Okay. So now what we did, so now this is very important. So now you can see here this is okay. Now what we are going to do, so now it's now in this example, now we are having an even function. So can you see here an even function? So the output is 1 if the number of ones is even in the inputs. Okay, now please remember, now we have an even function. This is an even function with 4 inputs. So can you see here, this is an even function with 4 inputs. So can you see here 0, control C, and then what I do, control A, this is del. Okay. Now what I'm going to do, I'm going to putting it here. Okay. Please remember now in this case, can anyone tell me now? Please remember, so this is now FE1. FE1 is a function of 4 variable, which is actually W, X, Y, and Z. So in this case, N is equal to 4. How many entries will be there in the truth table? So in the truth table, we will have 2 to the power 4, which is actually 16 entries. Yeah? Since we have 2 to the power 16 entries, 2 to the power 4, which is actually 16 entries. And now we want to count the number of ones. So we want to count the number of ones. So the number of ones are here. Number of ones. Can you see how many ones are here in this example? 0. Okay. Now we also want to go for the one. So if you look at this red one, how many ones are there? 2 ones are there. Here, how many ones are there? 2. How many ones are here? 2. How many ones are here? 2. How many ones are here? 4. Okay, now we want to look for the odd number of ones. How many ones are there in these two cases? 1 and 1. How many ones are here? 1. But now in this example, we also have here we have 2 ones. Okay, now if you go for this thingy, here in this truth table there are 3 ones, and in this truth table we have a single one. And now in this example, if we have this thing, the red color, we have 2 ones. Here we have 2 ones. Now in the green thingy, we have how many ones are there? We have 3 ones. And in this both example, we have 3 ones here and we have 3 ones here. So for the red one, can you see for all the red ones? So can you see for all the red ones? So these are these 3, 4, 5, 6, 7, and 8. So there are all the numbers of ones are even. Since the number of evens, so this F1 will be 1. So can you see here now? It's 1, it's 1 here, it's 1 here, it's 1 here, it's 1 here, and it's 1 here. Okay, now how can we write FE1? Yes, please help me. I want your answer now. Anyone may answer. How can we write Fe1? 6 sigma m. Yes. Can you help me?
0,
0. Very good.
3,
3. Then what?
5, 6,
5, 6. Very good. Very good. 5, 6, 7, 8,
9,
9,
10,
9, 10,
12, and 15.
12, 15. So now this is an even function. So now this is how we calculated it. So can you see here? So this is all these things. And how can we calculate even function? This is very simple. This is very simple. So what is Fe1? And it's very, very simple. So Fe1 is now, so this is actually, what are the inputs? So W is equal to or X is equal to or Y is equal to or Z, and this is whole bar. This is, and that you can compute it directly. Okay, so you can compute it directly. So what I'm going to do, so now I'm going to rub everything off. And now, please, I need your attention here. This is very tricky, and this may be the question in your next evaluation. So assume anyone. Assume we have a black box, and assume we have some inputs. So the inputs are, let's assume the inputs are A, B, C, D, E, and F. And we want to compute Fe1, and now we want to compute F odd. What will be the expression for F odd? Can anyone tell me? Yes. Now please remember, in this case 1, 2, 3, 4, 5, 6. So it means that we have now n is 6. So n is 6, we will have 2 to the power 6, which is actually 64 entries in the truth table. But we can compute F odd using exclusive OR. How can we compute F odd? Can anyone tell me? Yes. What will be the expression for F odd? Help me.
A XOR B XOR C.
Yeah, A exclusive or B exclusive or C exclusive or D exclusive or E and exclusive or F. And what will be Fe1 now? Please remember, Fe1 is equal to F odd bar, or F odd is equal to Fe1 bar. So how can we compute Fe1? Yes, Fe1 is what? Help me.
A XOR B.
No. You can use all the exclusive OR function. D, exclusive OR E, exclusive OR F, and then put a bar on the output. So this is very simple. This is very simple. You use all the exclusive OR gates. And then you put a bubble in the end. This is the most easy implementation to the most easiest implementation for an even function. Any question? Any question? Should we proceed? Should we proceed or not? Any question? I'm not hearing
No
anything
questions.
from. No question. Okay. Now I'm giving you another example. So let's assume we have this. W, X, Y, Z, P, and we want to compute F odd. Yes, what will be F odd? Help me. W,
X or X,
Y,
Y, Z.
Z, exclusive or P. And what will be Fe1? X odd bar. Whatever is this, you put a bar over the whole thing. Clear? Any question? Should we proceed?
Yes.
Okay, now what we are going to do now? So now, okay, now this is only now this is how can we compute an even function and how can we compute an odd function giving the number of inputs. Okay, so whenever we have any inputs, we exclusive or all of them, and please remember there is no exclusive OR gate with a multiple input. The exclusive OR gate is a 2-input gate. It's a 2-input. It's not a 3-input gate. It's not a 4-input gate. So exclusive OR gate is a 2-input gate. Please remember this. Okay. So now what we are going to do? So what is our objective now? our objective is now, and this is the rule for the parity generation in the checker circuit. Okay, now what we are going to do, so we want to generate the parity on the transmission side, and I already explained it to you, that let's assume we want to transmit any data, we want to transmit any n bit data. So we generate the parity on the transmitter side, and on the receiver side we check that whether there is an error or not. So and if you are using an odd parity, so please remember, if you are using an odd parity, so we have to use an even function. And if you are using an even parity, then you have to use an odd function. I will explain this with an example. I will explain this in an example. So I need your attention here. This is very important. This is very important. So now we have two things. Now we are using an odd parity. So for odd parity, should we use an even function or odd function?
Even.
And for even parity, should we use
Odd.
function.
odd function? I will explain this now in an example. How? And please remember, I need your attention here. It's not, this explanation is not in the slides. So assume that we have data. So now we have, now what I'm doing, I'm now using the green color. And now we are on the transmitter side. We are on the transmitter side. This is my transmitter side. We have three inputs, X, Y, and Z. Okay, what is N here now? N is not 3. Okay, please remember, now we are using an odd function, odd parity. We are using an odd parity. And then we want to generate a parity P bit. So now we want to generate a P bit parity. Okay, should we use an even function or odd function for this? Help me.
Even.
Even function. Since you are using an even function, how can we compute P? What will P in this example?
X, XOR Y, XOR Z whole bar.
And we transmit this data. Now we have a receiver side, and receiver side, now I'm using a black color. On the receiver side, I receive the data, because we are not only sending the data bits, so these are the data bits, X, Y, Z are the data bits. And in addition, we also receive a parity bit, P. So we also receive the P bit. And then we want to compute the error. And since it is an odd parity, should we use an even function or odd function? Help me.
Even.
So we should use an even function. And then how can we compute error? So now error is a function. So now how can we compute error? Error is equal to what? Can you tell me? So error now depends on X, Y, Z, and P. So how can we write it? X exclusive OR, Y exclusive OR, Z exclusive OR, P, and then what?
Whole bar.
Whole bar. Okay. And then we can see that whether there is an error in the data or not. I will explain this with an example. So please remember, this is very important. And I need your attention. Here. Okay. Now let's assume, so this is an example. And please remember, this is very important. So if you not pay attention, you may face some problem in the exam. This may be the question in exam. Assume that we want to send X, Y, Z. So assume X is 0, Y is 0, and Z is 1. Okay, we want to send this data 0, 0, 1. What will it be? So now we want to compute P. So P is actually 0 exclusive OR, 0 exclusive OR, 1 and whole bar. This is 1, so 0, 0 and 0, 1, 1 bar, it is actually 0. So this will give me 0. Since we are using an even function, so P will be 0 because we are using an even function. Yeah, now P is 0. Now we transmit this data. So now the data bits are 0, 0, 1. So this is actually 0, 0, 1. And what is the value of P now? P is now 0. Okay. Now is the data correct or incorrect for this example? We assume that there is no error in the data. The data is correct. So if we compute the error, so now we want to have the even function. So now how many number of ones are there? So it means, so can you see here? Now if you compute the error on the output, so this is actually 0 exclusive OR, 0 exclusive OR, 1 exclusive OR, 0 and whole bar. And if you compute all of these things, so this is actually 1 bar and it is 0. So it means that there is no error in the data. There is no error in the data. because now whatever the data has been sent and receiver, so it means that the receiver will not ask for retransmission. It does not ask for retransmission, and there is no error in the data. Any question? Any question? Okay, now what I'm going to do, now I'm going to rub everything up. So now can you see here? So now let's assume, so now assume that there is an error in X. If there is an error in X, and because of the transmission line, so we are sending it to a transmission line, and this X becomes 1. So on the receiver, now what we receive 1 and 0, 1, and what is P? P0. Now in this case, on the receiver side, what we receive 1 0 1 0. It means that now there is an error in which bit? Help me.
X.
Error in X. So how can we compute? So what is now value of X? X 1 is to your Y is 0, Z is 1, and P is 0. And since it is an even function, so the function is even, so this is actually, the error will now be actually 1 is to your 1 is 0, and 0 bar is equal to 1, and it means it will give me an error. Any question? Any question? Okay. Now what I'm going to do, and please, I'm now making a very tricky question. I'm making a very tricky question, and now I will, you know, and then you can say, now this is a tricky question. So Control A and Z. So now let's assume a scenario. Let's assume a scenario. So this is my scenario, and let's assume we want to implement an even parity. And the inputs are A1, A2 until AN. Now we want to compute P. Since it's an even parity, please remember, it is an even parity. Should we use an odd function or even function? Help me. Please
Odd.
remember it's an, so we should use an odd function. How can we compute P now? Yes.
A1 XOR A2 XOR AN.
A2 exclusive and blah 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 until what?
AN.
AN. Now we are on the receiver side. What will be the input to the receiver side? Yes. So now in this case, in this example, we have n data bits. Now in this case, we have n data bits. So n data bits. So we will receive an n bit data bits. So this is actually A1, A2 until AN. And in addition, we receive the parity bit, which is P. And the output should be now an error. So this will an error. Okay. Since we are using an even parity, should we use an odd function or even function?
Odd.
So we will use an odd function. Okay. Now, how can we compute error? Help me. How can we compute error? Error is what?
A1 XOR A2 XOR AN XOR P.
And then we also, in the end, we also want to have an XOR P, and then we put a whole, not whole bar, because we are using an odd function. So this will be an error. Okay. So if you are using an odd parity, so we put a bar on P and we put a bar on error. So this is the difference between the odd and the even function. Any question? Any question? Any question? Should we proceed? Yes.
Yes, sir.
Okay. Okay. Now what I'm going to do, so now, okay, now here, I haven't covered one topic. Remember, in the last lecture, I didn't cover one topic. And what was that topic? So that topic was, and then I'm going to cover that topic now. Okay. So I didn't cover this topic. So I'm going to cover the topic from my last lecture. Which lecture was this? Lecture 5? Yeah. I covered it for the next, for the previous for other section, but I didn't cover it for you. So this is the topic from the last lecture. So I didn't cover it, so now I'm going to cover it now. Now, multiple outputs. Suppose we have two functions. So can you see here? Now the first function, f. F is a function of three inputs, a, b, and c. And g is also a function of three inputs, a, b, and c. So these are two separate circuits. So in this case, there are two separate circuits. And in the other case, we have one circuit with two outputs, and now it's a combined circuit. So let's assume we have this function given f. So can you see here f? Now, if you want to draw the chem map of f, what is this thingy? It is actually 0, 1, 0, 2, 6, 7. So can you see? I'll solve it here. Now, what I'm going to do, I'm going to solve it here. So now this is my function. Okay. Now we want to solve for f. Okay. How the Carnot map will look like? Help me. 0, 1, 3, 2, 4, 5, 7, 6. Yes. Now we want to implement f. Which is the red color. This is a and b and c. Okay. So this is 0, 2, 6, 7. So 2 is 1. 6 is 1. 6 is 1. 0 is 1. And 7 is 1. Any question? Am I right or not? So then it's actually 0 and then 1, then 0, 0, 0, 1, 1, 1, and 1, 0. Now if we draw this thing, so basically, can we do this? So we have the first group, and then we have the second group. What is the expression? What is f now? F is now the green color. If you look at the green color, so the green color is
bar,
A bar.
bar.
A bar, no, C bar. Plus. And then if you look at here, so this is actually the blue color is A, and then now we want to solve for G. I now want to solve for G now using the green color here. Now, can you see here 0 and 1? So 0, 1, so this is actually 0, 0, 0, 1, 1, 1, and 1, 0. If it's 0, 1, so it is actually 1, 3, 6, 7. 1, 3, 1, 3, and then 7, 6, 7. So 6, 7. So now we can do this thing. So this expression will give me what? AB plus, and this expression will give me, can you see here? This one is actually give me A, this is A, so this is A bar. A bar what? Help me.
C.
What is the common term here in these cases? What is the common term here? So this is the common term. AB is the common term. So AB is the common term. So we can share the logic. So can you see here now in this example? So now we do with the minimization technique. So can you see here? So now if you draw this K map, the first K map, which is A bar C bar, and then you can see A bar C plus AB. So if you draw these circuits separately, for F and G, and how many gates are required? 1, 2, 3, 4, 5, 6. 6 gates are required. But if you see this AB, this is a common term. So instead of using 4 AND gates, we can use 3 AND gates, and we can share the logic. So the common term is AB. So we can see A bar C bar, and then AB. So it is shared. So how many gates are now required for the combined implementation? So in the combined implementation, we need 5 gates, and in the separate implementation, we need 6 gates. So E1, please remember, E1 Carnot K-map will give you the minimized expression. So if we have two multiple functions, and we have multiple functions, and multiple functions are solved separately, when one function are solved separately, it will give us minimized expression, but still it will not be the minimal implementation. So after that, what should we look for? We should look for some common terms, and when we go for this common term, we can draw an efficient circuit. Any question? Should we proceed? Okay, now this is another example. So can you see here, Okay, now there are two functions. There are two functions, f and g. F is a function of 4 variables, okay, and g is also a function of 4 variables. Okay, and how many ones are there in the KMF for f? 1, 2, 3, 4, 5, 6, 7. There are 7 ones in f, and in g 1, 2, 3, 4, 5, 6. There are 6 ones. So we draw the KMF. We draw the KMF of f and g. So can you see we draw the KMF and we find the expression. Okay, I'm not going to repeat this because you know you already did it before, how to draw the KMF and how to get the minimized expression. So now this red thingy is a bar bd. Now we have another group which is the blue thingy, this is the blue thingy, and this is the green thingy which is actually AC. And similarly we have found an expression for BD. What is the common expression here now? Can you see here? Now in this example, so can you see here? What is now the common expression here? Can you all tell me what is the common expression here? Anyone may speak. Yes, please answer me. It looks like that I'm talking to myself.
Professor, there is AC.
Yes, there is AC, and this is also another common term.
A bar D.
Is it also A bar D?
A bar D, yeah. So how can we write G? So can you see here G? G is actually, so can you see here? So now we can write G. G is equal to, so we can say, okay, now I'm using this color, the red color. T1 plus, and then we have this, can you see T1 plus T2 D bar. What is now T1 here? So T1 is now, T1 is A bar D, and T2 is now what? Tell me. AC. Now, how can we write F now? So F is actually what? So we can rearrange because it's the A bar D. So I can rewrite it. So I'm now rewriting it. So A bar D B plus, because it's commutative, then I'm writing AC. What is AC? AC is now T2. So this AC is now T2 plus CD, and in your CD we can write CD as it is. Okay, now what is A bar D? A bar D is T1. So what is now F? So F is now, can you see here? So this is T1B plus T2 plus CD. So now we can share this common term for the other thing. So if you implement this thingy, we are deriving this common term. So we have this. Any question? So now when you do that, so now if you implement this thingy, so here now in this F we require a 3-input AND gate. Here a 3-input AND gate. How many gates are there? 1, 2, 3, 4, 5, 6, 7. And in the combined implementation, 1, 2, 3, 4, 5, 6, 7. Oh, the number of gates are same. But in the first implementation, we require here 3-input AND gate, and here we require a 2-input AND gate. So basically, now we have reduced the number of inputs to the gates, and it will have less delay. Please remember, a 3-input AND gate has more delay than a 2-input AND gate. So now we have reduced the number of resources, and we have further minimized the circuit. Any question? Any question? Yes. So now what's the summary for KMAP? So now this lecture is now finished. Lecture number 5, the minimization technique. It's also called as KMAP for short. The KMAP is a diagram made of squares. It is a reorganized version of the truth table. Each square in the KMAP represent a main term. Adjacent square differ in the variable only of one variable because we are using the gray code. And simplified expression can be derived from the KMAP by recognizing the pattern of squares. We can have a square of 1, square of 2, square of 4, square of 8 or 16 or so forth, so on. And if you want to find a simplified SOP expression, we are using an AND OR circuits and simplified POS expression or AND circuit. Any question? Any question? Okay. Now let's assume now we have something. So should I rub this off? Let's assume now we have some expression f. Let's assume we have some expression f. So can you see here? Let's assume we have, if we have ab plus cd plus bs. This is my f1 now. Now if you draw the implementation for this, how will it look like? A, B, C, D, and then we have the A bar, B bar, C, then it is actually C, D, and then this is actually A, B. And then we combine them, this is an R. And let's say we have F2 now. Let's say F2 is actually AB A, I'm using the black color, AB plus A bar C plus B. Now if you look at F2, so F2 will first contain AB, then it is A bar C, and then we have BD. Now if you look at here, how many gates are required for, if you treat them separately? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 gates now. How can we implement them efficiently? Yes. Can you tell me what is now the common term?
AB and A bar C.
Yeah, AB is the common term. Since AB is the common term, so what we are going to do, so we can rub this off. So now I'm not using the color, so I can use it. AB is now the common term. Since AB is now the common term, so what I can do, so I can put a bar from here. So now I can put a bar from here, and then I directly connect it to here. Any question? So this is now the common term. This is now done. And then what is now the common term?
A bar C.
A bar C. So now A bar C is the common term now. Since A bar C is now the common term, so now this is the common term. Now this is the common term, and then we can see A bar C is now the common term, and then now we put it here. So A bar C, and I'm putting it here, A bar C. And now what I can do, so now I can rub this off. So now, because this is A bar C, so now I can rub this off. Any question? So now we have now reduced the, so in the previous implementation, we have 8 gates. Now how many gates do we have? Yes, in this example.
7.
We have reduced the number of gates from 8 to 7, from 8 to 7 gates. And in the previous implementation, we have 1 3 input AND gate. But now in the new implementation, we have reduced, we have replaced that 3 input AND gate with a 2 input AND gate. Any question? Any question?
No, sir.
Okay, very good. So now this is how it works. Now coming back to the generator circuit. So now this is on the generator circuit. So now we have the parity generation circuit. A parity bit is added to the n bit code. It produces n plus 1 bit code with an even or odd number of 1. For odd parity, we have to use an even function to generate the odd parity bit and use an even function to check the n plus 1 bit code. So this is actually the parity generator for what? Even parity or odd parity? Help me. Can you tell me?
Even parity.
Why it's in even parity?
Because it's 2 XOR gates, which are odd functions.
Yes, it is an even parity because it's an even parity generator, because we are generating the parity bit. So because we are using an odd function, Now on the checker side, so we send the transmission, the data bits. What are the data bits? X, Y, Z, and in addition to the data bits, we also send the P bits, which is the parity bit. And now since it is an odd function, so we also, it is, what is the odd function? What is E? E is actually P exclusive or X exclusive or Y exclusive or Z. And now given an example. So given an example, so let's assume we have the input is, let's assume the input xyz is 0, 0, 1 and parity, then it means that now xyz 0, 0, 1, this is xy 0, 0, 1. So now the parity bit is now 1. So we send the parity bit along with the data bits. So now what is now p? P is 1 and the data bits is 0, 0, 0, 1, 0, 0, 1 now. Okay, let's assume y changes from 0 to 1. Y changes from 0 to 1. So now the value of y is 0 here, and now it is changed to 1. And if we compute the e bits, so what is it? Is 1 exclusive or 0, which is 1, and 1 exclusive or 1, it is 0. Okay, and 0 exclusive or 1 is 1. So the error e will be 1. It means that it will now indicate an error. It means that now there is error in the transmission. And what should now the receiver does? Yes, what should do the receiver does in this scenario? Can anyone tell me what should the receiver does in this scenario? Anyone?
Will it request for the data again?
No, it should ask the transmitter to retransmit the data. Clear? So it will ask the transmitter to retransmit the data. Any question? Any question? Should we proceed?
No, sir.
Why?
No question.
No question. I was confused. Should we proceed? Okay. Okay, so I will do the hierarchical design later on. But now I'm going to do, so please, you will solve me, I will give you one problem and now you will tell me the solution for this thing. Okay, Control A. So this may be the question in exam. This may be the question in exam. Assume that, so now this may be the question in exam. So what I'm going to do, so assume that, so this is the maybe the question in exam. Assume that we are sending 5 bits, okay, namely A, B, C, D, and E, and we are using an odd parity compute P on the transmission side and compute error on the receiver side. Yes, this may be the question in exam. Or in other words, design, the question may be this, design and this may be, I can also compute P on the transmission side or compute error on the receiver side, and I can reformulate design an even, no sorry, design an odd parity, sorry, design an odd parity generator and design an odd parity generator and checker circuit for a 5-bit data, namely A, B, C, D, and E. Yes. Yes. How can we do it? Anyone may answer.
Professor, by compute, do you mean the expression?
Yeah, I may ask
Compute
for
P on the
yeah, I may ask for the for the expression, and I may also ask for the circuit. So if we see, now we want to compute P. What is P? Anyone?
A X nor B X nor C X nor D.
Is this your C? Is this your what?
D,
Is this your
E,
E?
and
And since
whole
are
number.
we using function or even function?
Or even functions, so whole not.
Even function. We'll put a bar here. Okay. And now what will be error? Yes. Yes. The whole thing. P is also there. How can we compute the error? Okay, please remember this is how can we compute the error. So if you want, I ask you to draw the circuit, so it will be some circuit like look like this. A is your B. Okay, then what you can do? Please remember there is no 6 input OR gate. So this is exclusive OR D, and then you can use another exclusive OR for E and exclusive OR P. I'm computing now the circuit for parity. So it will go to another exclusive OR gate. Got it? And then it will go to another exclusive OR gate. And it will give me an on the receiver side or transmitter side, the green color. Help me. And now on the transmission side. So now this is the complete design. So
Professor, shouldn't there be
Yeah.
a not at the end?
yes, that was the reason. You know, I think that you're now. I was checking that whether you are awake or you are sleeping. It means that someone is awake. That's good. That's good. Thank you. Okay. So now what we are going to do on the transmitter side. So on the transmitter side, what we have is exclusive or A or exclusive or B. Then we have what? C exclusive or D. Then we have another exclusive OR gate, and then we have another exclusive OR gate, which is what? Yes. Then we have E. Yes,
E.
A, B, B, and then we put a bar in the end. So this will give me a P. So this is my transmission side, and this is my now receiver side. Any question? Any question?
No question.
Is it clear?
Yes, Professor.
Okay, so now what I'm going to do now, so now I'm going to have, and I'm now stop recording.